Welcome to our Quantum Deep Dive. Today we're plunging into the world of hybrid quantum classical optimization, often just called HQCO.
Right.
And this deep dive is really fueled by a detailed essay from Jurgo Schneppat. It's titled Hybrid Quantum Classical Optimization, Effizienz steigern.
A really interesting piece.
Definitely. So our mission today is pretty clear. Let's try to distill the key insights from this source, understand what HQCO actually is, why it's so relevant right now, and, maybe peek into its future, all specifically for you.
Yeah, and one of the things that jumps out right away in the essay is that HQCO isn't just like another cool quantum idea. Schneppat really presents it as a practical necessity.
A necessity.
Yeah, something needed right now because of the limits he sees in both classical computing and the quantum hardware we have today. That's a crucial point. It's a solution born out of current constraints.
Exactly. That really sets the stage for the why now question. So let's dig into that. The essay argues classical computers kind of hit a wall with certain complex problems. What types are we talking about? Why do they struggle?
Well, it highlights things like problems with really high dimensional spaces, tricky non-convex optimization landscapes, and especially those combinatorial nightmares. Think traveling salesman or max cut.
The classics.
Right. And the big challenge is scaling. For these kinds of problems, classical methods often just become incredibly slow, needing computation time that just blows up exponentially as the problem gets bigger.
Okay, so classical struggles with scale. But on the flip side, our current quantum computers aren't miracle machines either, are they? The essay calls them NISQ era tech.
Precisely. NISQ, noisy intermediate scale quantum. That tells you a lot right there. They're susceptible to errors, noise from the environment messes things up. They don't have a huge number of qubits yet, and the qubits they do have can't hold their quantum state for very long coherence. Time is limited.
So they're not quite the fault-tolerant powerhouses we sometimes imagine for the future?
Not yet. And that's why the essay makes such a compelling case for HQCO. It's framed as a way to actually use the potential of today's quantum hardware, even with its flaws, by smartly pairing it with what classical computers do really well. It's all about building that bridge between the two.
Okay, that makes sense. Classical struggles with scale, quantum struggles with noise and size. So the hybrid idea must be about splitting the workload, playing to their strengths. What are the benefits Schneppat points to?
The key benefit the essay focuses on is getting efficiency gains. The idea is let classical computers handle the parts they're good at, things like prepping the data, maybe doing some sophisticated error checking or mitigation, and definitely managing the overall process, like the iterative loops.
Okay.
Meanwhile, the quantum computer gets handed the specific, really tough computational bits of the problem. The parts where its unique features, superposition, entanglement, might offer a way to explore solutions faster or find better approximate answers by looking at many possibilities at once.
So it's a division of labor.
Exactly. And the hope is this leads to, potentially faster computation times compared to just using classical methods, maybe finding better approximate solutions than classical could alone in a reasonable time, and also boosting the fault tolerance a bit because the classical side can help manage or correct for the quantum errors.
That division of labor really sounds logical. Optimize the whole thing by using the right tool for the right part of the job. Now, before we get into the specific algorithms, the essay does a quick recap of the basics. What classical and quantum concepts does it stress are important here?
On the classical side, it's pretty much standard optimization territory, trying to find the best settings, the best parameters to make some function as low or high as possible. The essay mentions gradient-based methods like gradient descent.
Right, following the slope.
Yeah, exactly. And it also covers heuristic or meta-heuristic approaches, things like simulated annealing or evolutionary algorithms. Those are useful when you don't have a nice gradient to follow, using more like trial and error or nature-inspired search tactics.
And the quantum building blocks for optimization.
The essay highlights the key players. Qubits, first off. Unlike classical bits being just 0 or 1, qubits can be in a superposition, a mix of 0 and 1 at the same time. That allows for representing and potentially exploring way more possibilities simultaneously.
Okay.
Then there's entanglement. That spooky connection where qubits are linked, and measuring one instantly affects the others no matter how far apart. It's crucial for the power of some algorithms. And finally, measurement.
The act of looking at the qubit.
Right. That collapses the superposition down to a definite 0 or 1. You need it to get an answer, but it also changes the quantum state. For optimization, this often means you have to run the quantum part many, many times to build up statistics and get a reliable signal out of the noise and randomness measurement introduces.
Right. So we use these quantum tricks, but we need the classical side to handle the messiness and limitations. And this leads us right into those key hybrid algorithms Schneppet focuses on, VQE and QAOA. Let's start with VQE, the Variational Quantum Eigensolver. What's its main job, according to the essay?
VQE was really born out of chemistry problems, specifically finding the lowest energy state, the ground state energy of molecules. This is super important in quantum chemistry and material science for understanding how stuff behaves at the atomic level, or even designing new molecules or materials.
And how does the hybrid part work for VQE? Where does classical come in?
This is where the classical optimizer is absolutely critical. So the quantum computer runs a quantum circuit, one that has adjustable knobs, parameters. This circuit prepares a quantum state that's supposed to be an approximation of the molecule's state. Then you measure its energy.
Okay.
That energy value gets fed back to a classical computer running an optimization algorithm. The essay mentions things like gradient-based optimizers, Atom is a common one, or maybe evolutionary strategies, even Monte Carlo methods. This classical optimizer looks at the energy and figures out how to tweak the knobs on the quantum circuit for the next run to try and get an even lower energy.
So it's a loop. Quantum computes energy, classical adjusts parameters, repeat.
Exactly that. It's an iterative loop. The quantum computer does the heavy lifting of calculating the energy for a given state, which is hard classically, and the classical computer does the intelligent searching through the parameter space to find the state with the minimum energy.
So the quantum part prepares the state and measures. The classical part does the smart searching.
Precisely. And the essay gives examples like calculating the energy of a water molecule, HOs, or using VQE to help simulate new materials. It really plays to VQE's strengths.
Okay, that makes sense for VQE. What about the other one mentioned, QAOA? Quantum Approximate Optimization Algorithm. What kind of problems is that aimed at?
QAOA is specifically tailored for those tricky combinatorial optimization problems we mentioned earlier. Things like the max cut problem, trying to divide nodes in a network into two groups to maximize the connections between the groups.
Right, another hard one. And the hybrid loop for QAOA, similar idea.
A very similar pattern, yes. The quantum computer runs a different kind of parameterized circuit. It builds up a quantum state by applying a sequence of operations, usually alternating between two types, often called problem and mixer Hamiltonians, each with their own parameters.
Okay.
Then you measure the outcome. For max cut, you'd measure something related to how many edges you successfully cut. That result, or score, is passed back to the classical optimizer. Again, the essay lists examples like gradient methods, genetic algorithms, maybe Bayesian optimization. The classical part's job is to find the best settings for the parameters in those quantum operations to maximize the score to find the best cut in the max cut example.
So again, it's the classical optimizer doing the iterative refinement based on the quantum computer's output. Both VQE and QAOA really depend on that classical piece to make them work effectively, especially with today's noisy hardware.
Absolutely. That classical loop is essential for navigating the limitations of NISQ machines.
Now, actually running these hybrid systems needs specific tech. What does the essay say about the hardware landscape and the interfaces needed?
It covers the main types of quantum hardware people are using or developing for HQCO. You've got the gate-based systems, the ones that use sequences of quantum logic gates. Companies like IBM, Google, Rigetti are big players there. Then there are quantum annealers, like the machines from D-Wave. These are a bit different. They're special-purpose hardware designed specifically for a type of optimization called adiabatic optimization. They're not universal quantum computers like the gate-based ones, but potentially useful for certain optimization tasks relevant to HQCO.
And given these different types, often accessed over the internet, interfaces must be key.
Crucially important. The essay really stresses the need for solid interfaces between the quantum and classical parts. Often this happens through cloud platforms. Think IBM Quantum Experience, Amazon Bracket, Microsoft Azure Quantum. They provide access to quantum processors remotely. Integrating these with powerful classical computers, maybe high-performance computing clusters, is also mentioned as being important for complex workflows.
And what about the software, the tools to actually build these hybrid algorithms?
Yeah, the essay touches on specific software frameworks that help bridge this gap. Things like IBM's Qiskit, there's PennyLane, which is a Python library popular for quantum machine learning, but it works very well for the parameterized circuits in VQE and QAOA2 and Google Circ.
Right.
And it makes the point that programming these hybrid systems isn't just about writing quantum code. It's often about writing classical programs that strategically call quantum subroutines, or classical algorithms that manage and update the parameters being sent to the quantum hardware.
It sounds like a pretty complex integration challenge. What does SNEPHAT highlight as the major hurdles in making HQCO really practical?
The essay lays out several big ones. Decoherence and noise are still fundamental headaches. Quantum states are just incredibly delicate, easily disturbed by the environment, which leads to errors in the computation.
Still the main enemy.
Pretty much. Then there are scaling issues. Today's quantum computers just don't have that many high-quality qubits. Not enough to tackle the truly massive problems where classical computing completely bogs down.
And you mentioned the software side just now. Are there challenges there too?
Oh yeah. Software development itself is a bottleneck, according to the essay. There's a lack of standardization. Code written for one company's hardware might not easily run on another's. Latency is a big one too.
In delay.
Exactly. The time it takes for the classical computer to talk to the quantum computer and get a result back. In those tight iterative loops like in VQE or QAOA, that round-trip time can really slow things down. And finally, the limited fault tolerance we talked about. Getting reliable answers from complex quantum circuits is still tough, and it often relies on clever classical techniques for error mitigation.
Okay, so we've got the what, the why, the how with VQE and QAOA, and the challenges. Where is HQCO actually being put to work, or at least seriously explored right now? The essay gives some concrete examples.
It does. It points to several sectors where people are actively experimenting. Finance is a big one.
Makes sense. Lots of complex optimization there.
Definitely. Companies like JP Chase, Goldman Sachs are mentioned as looking into HQCO for things like optimizing investment portfolios, managing financial risk, pricing complex derivatives, problems with potentially huge numbers of variables.
What about logistics? Things like routing.
Logistics is another key area highlighted. Route planning, optimizing supply chains. These are textbook examples of combinatorial optimization where HQCO might help. The essay mentions Volkswagen looking at optimizing traffic flow and DHL exploring routing problems.
And VQE seemed tailor-made for simulating molecules.
Absolutely. That's a major application area in material science and chemistry. The essay notes companies like Pfizer and Merck investing in this space, using HQCO, particularly VQE, to simulate molecular behavior, hopefully speeding up the discovery of new drugs or advanced materials.
And artificial intelligence.
Right.
Optimization is everywhere in AI.
Indeed. The essay touches on quantum-enhanced machine learning. People are applying HQCO techniques to optimize parts of AI models, maybe making training more efficient or helping find better model structures.
Okay, one more area mentioned was complex networks.
Right. Things like telecommunications networks or electrical power grids. HQCO offers potential tools for optimizing how these massive, interconnected systems are configured and how resources are allocated within them.
Wow, that's a really diverse set of potential applications. It shows the breadth of where this could go. So looking ahead, what's the essay's take on the future? Where might we see improvements, and what are the hard limits?
The essay seems, cautiously optimistic about improvements. It anticipates better quantum hardware, obviously more qubits, better quality qubits, better fault tolerance are all essential. It also expects more sophisticated hybrid algorithms, maybe ones that adapt on the fly or use more advanced classical techniques. And better software tools and integration are seen as crucial for making it easier to build and deploy these applications.
But it's not all smooth sailing, right? What about the limits?
No, it's definitely realistic about the limitations too. The essay is clear that HQCO isn't going to magically solve every optimization problem. Not everything gets a quantum speedup, and classical algorithms will still be the best choice for many, many tasks.
Right.
And those core challenges, noise, fault tolerance, they aren't disappearing overnight, even with hybrid approaches helping manage them. Scaling the communication between the quantum and classical parts, that latency issue will remain tricky. And energy efficiency, especially the cooling needed for some quantum hardware, is still a practical consideration.
So given all that, what's the prognosis from SNEPHAT for, say, the next decade or two?
Okay, so for the next 5 to 10 years, the prediction in the essay is that we'll see more practical, real-world uses emerge, probably driven by easier access through the cloud platforms. It expects the first serious steps towards actual fault-tolerant algorithms and maybe the start of real commercial adoption in some of those niche areas we talked about, like finance or materials.
And longer term, 10 to 20 years out.
Looking further ahead, the vision outlined is for hardware to become much more scalable and stable. HQCO could then potentially start tackling problems that are currently considered genuinely unsolvable by classical means within a practical time frame. There's even talk of possibilities like self-learning quantum AI systems, or maybe the emergence of tightly integrated universal quantum classical supercomputers.
That's quite a future vision. It sounds like the essay's main takeaway is that HQCO is especially valuable right now, acting as that necessary bridge while the quantum hardware catches up.
That really feels like the core message. It's a promising path because it lets us start tapping into quantum capabilities today with the imperfect hardware we actually have. But as the essay makes very clear, its ultimate widespread success really depends on cracking those tough hardware and software challenges.
Yeah, this deep dive into Yogo Schnepat's essay has really painted a picture of hybrid quantum classical optimization as a very pragmatic field. It's actively evolving, driven by the real-world constraints and possibilities of computing right now.
It definitely highlights how progress often comes from cleverly combining different approaches, doesn't it? Not just betting everything on one technology.
Exactly. And as this deep dive into Yogo Schnepat's essay shows, the next 2 decades could see problems we currently consider unsolvable finally find their solutions through these hybrid methods. It really makes you wonder what seemingly impossible challenges might be unlocked by this evolving partnership between classical and quantum computation. Thank you for joining us for this deep dive. Goodbye.